We'll continue today looking at transformations, except today we're going to use matrices to help us with the transformations. Some of you won't find them a help. In fact, many of you will find them a hindrance. Matrices are on the course. They've got to get them into the course somehow, and this is where they use them. There used to be a better application, Markov chains, but now this is it. So you can pretty much guarantee that this is going to come up on the exam. So take note. Transformations are about moving points on a plane or mapping a set of points. So remember that the originals, or technically the pre-image, to x dash and y dash the image according to some sort of rule. We use a transformation where we've got r squared maps to r squared on the exams. I'm actually not sure really what that actually means and why they use different notation, but it's to indicate that a transformation is a mapping from the Cartesian plane into the Cartesian plane. So you don't really need to worry about this notation at all. I'll show you some questions where they use the notation and show you how to sort of work your way around it. So the following table gives a summary of some basic transformations. So when we're reflecting in the x-axis, recall that what will happen is we do this, x comma negative y, and that could actually be written as follows. So we would have x plus 0y. So we could say that x dash equals x plus 0y, x dash equals x. And this one we could say y dash equals 0x plus negative y. All right, reflection in the y-axis, that's just going to be negative x comma y. So we could say this, x dash is equal to negative x. Remember, that's x dash and that's y dash there. Y dash is equal to y, or we could put a 0y and a 0x in there and rewrite the same thing. So x dash is that and y dash is that. Now, why are we doing this? Why are we making it look more complicated? Well, this basically forms a structure of the matrix that we're going to use to conduct the transformation. Okay, dilation factor K from the y-axis is this. So what we would do is dilations from the y-axis change x. So that's going to be kx, comma y. X dash is equal to kx, y dash equals y. And we could throw some zeros in there to write the same thing. Right, so we'll continue, or it continues in this way. Reflection in the line y equals x, or we're going to say the inverse is done like this. X dash is equal to y and y dash is equal to x, i.e. swap x and y. And we can also do translations by using this particular column matrix. All right, so let's have a look here. So what the first five are there, the first five mappings given in the table are special cases of a general kind of mapping defined by x dash equals ax plus by and y dash is equal to cx plus dy. Where A, B, C, and D are real numbers. And what we can do, you'll note, is that this A can be placed in a matrix, this B can be placed in a matrix, this C into the matrix, and this D into the matrix. So it forms a 2 by 2 matrix. And you'll note that you can use this matrix. So I can say that this x dash equals, now you might remember from last year, or particularly year 10, when we did matrix multiplication, we do this multiplied by this and that multiplied by that. We add them together. So we've got ax plus by, and y dash will be cx plus dy. Okay, if we multiply it out. And so you'll note that that is just that. Okay, so this is just another representation of this, except it's within a matrix. So this is what it actually represents. And we can actually convert these statements into a matrix by using the following. So reflection in the x-axis is going to be done using this particular matrix here. Okay, so pop a 1 there and a negative 1 there, so that when we multiply it out, so just say we've got xy and this is or equals x dash and y dash, what we're going to get is x dash is going to be x and y dash is going to be negative y. Okay, hence the reflection in the x-axis. Right, so all of these when multiplied out will give us the required transformation. DAB is used to denote a 2 by 2 dilation matrix where A represents the dilation factor A from the y-axis, B represents the dilation factor B. So this one here, what it would give us, so D34, I haven't really seen this notation. I've actually pinched this a few years ago off Mr. Tench's PowerPoint, and I haven't really seen it on exams, but it's worth noting that this is a representation or a construction of a dilation matrix. And what this represents, this 3 here represents a dilation factor 3 from y, and this one here is 4 from x. How do I know? 3, 0, 0, 4, and what we're going to do is multiply an ordered pair or a set of points to produce x dash and y dash, the image. So this x dash will be equal to 3x, and if I do matrix multiplication, 0y, and y dash will equal 0 times x, 4 times y is 4y. We pop that in mapping, 3x, 4y, x dash is equal to 3x, y dash is equal to 4y, and we can simply read that. That's a dilation factor 3 from y, 4 from x. Okay, so AB produces a translation matrix, A units in the X direction and B units in the Y direction. So this A value here will send it left or right, and then B value will send it up or down. So TAB is used to denote a 2 by 1 matrix. So this notation basically means it's a translation matrix going 1 unit to the left and 2 units up. So using matrix methods, so they're forcing us to use matrix methods. We can do this in a SAC as well. We can write using matrix methods, and you're forced to do it. So those of you who could do this without transformations, too bad. You have to do it with matrices if we ask you to do or use matrix methods. We are allowed to force a method here because, well, it's on the course. Find the image of the point 3, negative 2. So that's our x and y. That's our ordered pair. So 3, negative 2. Under a reflection in the x-axis. So reflections in the x-axis change y. So this is going to be the negative 1. Well, actually, let's not put 1. We'll put that in negative. A dilation factor k from the y-axis. Dilations from y change x. So that's going to be k there. And a translation 3 units in the positive direction of the y-axis or x-axis. So 3 units in the positive direction, 0 units in the either up or down. So now that we know that there's no dilation from the x-axis, we'll pop a 1 there, which indicates that it's just a reflection only. When this number is something other than 1, then it's going to be some sort of dilation factor. Okay, now what we do with these spots here is we just plonk zeros in them. Okay, and what that's going to give us when I multiply it out is our new values. Okay, so what we would do is we would say that this value here is going to be 3k plus 3. So 3k plus 3 is equal to k multiplied by 3. So k multiplied by 3 plus 3. 0 multiplied by negative 2 plus 3, right? So, yeah, just had to pause that video and think there. Yep, that's right. So that multiplied by that plus that multiplied by that is 3k plus the 3 equals that. Right, now let's do this one here. So 0 multiplied by 3 plus negative 1 multiplied by negative 2 is equal to 2. Plus 0 is equal to 2 still. Okay, so we've got our transform points. So 3 comma negative 2 will map to 3k plus 3 and 2 after these transformations. Now that's using matrix methods. We can also do a point-by-point transformation. So 3 comma negative 2 maps 2. So reflection in the x will negate y. So what we'll do is 3 comma 2. Dilation factor k from the y-axis. Dilations from y change x by the factor mentioned. So 3k comma 2. And translation 3 units in the positive direction of the x-axis is simply 3k plus 3, comma 2. Okay, so there it is via the mapping. There it is via the matrices. Now I know which one I like better because, well, one, I just had to really think about the matrices there. Haven't done them for a while, actually, to be completely honest with you. But there it is via point, point, point. So you can see here that I definitely prefer this method here, but we need to be comfortable with matrix methods. Okay, using matrix methods, find the image of the point 3, comma negative 2. So same point. Under a translation 3 units in the positive direction of the x-axis, a reflection in the x-axis, and a dilation of factor k from the y-axis. Okay, so 3, negative 2 is the point, the ordered pair. This is the transformation matrix, and what we'll get is the new point, the image. Okay, so translation 3 units in the positive direction of the x-axis. So that's going to be 3. There's no y or up and down, so we're not going to worry about it. A reflection in the x-axis, so reflections in x change y, so that's going to be negative. We'll hold off there and check whether there's a dilation from the x-axis as well. A dilation factor k from the y-axis, so that's going to be k, 0, 0, and 1 is going to give us our value. Now, does this look very familiar? Well, it looks exactly the same. So what's the difference? Well, the difference is this one here. What we have to do, we have to force it to do the translation 3 units in the positive direction of the x-axis first. Now, how do we do that? Well, in mathematics, girls, we want to force a calculation to go first. Say we've got this problem here. What's going to happen is order of ops is going to say, hey, we've got to do the multiplication first. So you want to force the addition, you've got to put some brackets around it. And it's exactly the same with this. So what we want to do is force the translation. So we stick some brackets around there. And what's going to happen is we're going to do 3 plus 3, which is equal to 6. And then we're going to do k multiplied by so I better show my working out for this. So this is going to be k, 0, 0, neg 1. We're going to add these together, and that's going to be 6 and negative 2 is equal to this. So k6, that's going to be 6k, and this one is going to be 2. Okay, so you'll note that the result or the transform point is different to this. This is 3k plus 3. This is 6k. Again, let's just try quickly a point-to-point transformation. So under a translation 3 units in the positive direction of the x-axis, so that's what we do first. K, what is it? A reflection in the x-axis changes y, 6, comma 2, and then k, factor k from y, so 6k, comma 2, which is exactly what we got there and there. Okay.
Okay, I'm just cutting this portion of the video in again because when I originally did this problem here, I actually made a mistake. And it's the reason I made a mistake is because I didn't read the problem carefully. And what we're after here is a linear transformation. Now, what is a linear transformation? Well, they're defined as follows. X comma y maps to ax plus by and cx plus dy. So x dash is found by doing that, and y dash is found by doing that. Now, what does that mean in this context? Well, you can actually write that in a matrix: A, B, C, D. X, Y produces x dash and y dash. And what you'll note is when I multiply it out, I get A times x plus B times y equals x dash. That's this here. Cx plus dy equals y dash. So what we need to be aware of is this kind of transformation is defined as a linear transformation. And essentially we're saying that you can only use dilations and reflections when we work with linear transformations. My mistake was that I added a translation matrix as well. And remember, if you do remember, what we did was we did this via a bit of sort of trial and error or guess and check. But we're not allowed to do that with a linear transformation. So let's get stuck into the problem. I've got a matrix A, B, C, D. I'm multiplying the point 0, 1, and I get negative 2, 7 out of it. So what that is going to mean is a times 0 plus b times 1. So a times 0 plus b times 1 equals negative 2. Or b is negative 2, and we've just found b. Alright, then what we'll do is c times 0 plus d times 1 equals 7. Okay, so that means that d is equal to 7. So we've found our b and we've found our d. Alright, let's do this other point here. So I'll set that up. I've got 5 and 2 coming out as the images when I dilate with A, B, C, D and reflect if that happens. And that is 5, no, 1, 0. Okay, so let's run it. So I'm going to get a times 1 plus b times 0 equals 5. So that means a equals 5. C times 1 plus d times 0 equals 2. That means c is equal to 2. So now I've got my full dilations matrix. So let's write in our values. It's 5, 2, and negative 2, and 7, I think. Yeah, 7. Multiplying by negative 2, 6 to get what? It's going to be 5 times negative 2 plus negative 2 times 6. So that's negative 10. Take 12. That equals negative 22. So that's negative 22 there. Right, we've got 2 times negative 2 plus 7 times 6. So that is 42, take 4 is 38. So that's 38. And there's our solution there. So negative 22 and 38. Right, so the operative word to look for to use this technique or to use only one of these 2 by 2 matrices is a linear transformation.
Transformation is defined by this matrix equation. So x dash is equal to ax plus b. So what that's going to look like, this is our x dash and our y dash equals a. This is this matrix here, 0, 1, 0, negative 2. And what we're operating on is x, y, plus b is negative 3 and 1. Alrighty, so what we'll do is we'll just note that via matrix multiplication, x dash is equal to x take 3, y dash is equal to negative 2y plus 1. Again, just using matrix multiplication there. Alright, here was my quadratic. Okay, so what I want to do is find x, or make x the subject and make y the subject. So x equals x dash plus 3, y dash, take 1 over negative 2 equals y. Okay, so your options at this stage, well, I was going to say you could kind of read off the transformations using function notation and pop them in, but yeah, don't know whether that's the way to go. So let's just pop our definition of y and x in. So that's going to be y dash take 1 all over negative 2 equals x dash plus 3 all squared plus 2 x plus 3 plus 3. All right, let's just tweak this a little bit and make it look a bit more pretty. So x, I'm going to drop my dashes, x squared plus 3 times x doubled is 6x plus 9 plus 2x plus 6 plus 3 equals y take 1 over negative 2. What I'll do is multiply all of these by negative 2 and collect up at the same time. So I'm going to have negative 2x squared, 6x plus 2x is 8x. 8x multiplied by negative 2 is negative 16x. Being a bit cocky here and doing a bit more than I like at once. 8x multiplied by negative 2. Yeah, I'm happy with that. All right, so I've got 9 plus 9, which is 18. 18 gets multiplied by 2, which is 36. Take away 36. Okay, so -2 multiplied by 18 is 36. And so that's y take 1, so we're going to add 1 to it. Y equals -2x squared, take 16x, take 35 after 1 is added to both sides. So there is the image after performing those transformations. Okay, other methods to do it. What you could do is read off these transformations. So I can see that this is a dilation factor 1, or it's not dilated. So this is going to be just an x take 3. This is going to be moving this function here 3 units to the left. So I could do f of x plus 3, pop that into the function, then start to build up my functions. So g of x equals that. H of x equals, so the next thing that gets done is it's reflected in the x-axis dilated by a factor of 2 and then translated up 1. So that's going to be -2 f x plus 3 and hij x equals -2 f of x plus 3 plus 1. So I think that will give it to us. Let's just have a play. This is not the way I do it, so I'm out of my comfort zone a little bit with this. I would absolutely do this via mapping, but I'm just going to test it out and see. If I get this horribly wrong, I'll debate whether I edited out the video or not. I need -2 multiplied by f of x plus, this is going to work, plus 1. Expand, yeah, there it is. Okay, so that's an alternative method to do it, is to convert that matrix into what you know about functions and just run it through function notation. Okay, so this again is the same problem, except note that what we've got is some brackets here. So we're going to go and write that out. So x dash and y dash are equal to 1, 0, 0, -2, x comma y, so just those general points on the original, plus -3, 1, where the equation says that that has to get done first. So x dash equals x take 3, and this one here is y dash is equal to y plus 1, y with 1 added to it, and then multiplied by -2. Right, so same process as last time, x dash plus 3 equals x, y dash over -2, take 1 equals y. Okay, so it feels like there's going to be not much difference here, but I bet there is. Yeah, there will be. All right, so we're going to get y equals, what am I doing? Here's my original, y dash over -2, take 1 equals x dash plus 3 squared. So I'm just subbing x and y on, plus 2, x dash plus 3, plus 3. All right, expand this thing out. So x squared, drop your dashes. What's it? 6x plus 9 plus 2x plus 6 plus 3. Y over -2, take 1. Okay, now I'm going to add 1 to both sides. Y equals x squared. So I've got plus 8x plus 18 plus 1 is 19. Now multiply by -2, y equals -2x squared. Take 16x plus minus, come on, Miss Noah, minus 38. Right, so are they close or are they similar? Yeah, they're similar. Right, one's got -35, one's got -38. Are they the same? No. All right, so here is a question from the methods exam from 2019. Tough question again. Ms. Cowan Ripper. this one. All right, so we've got this function here. F is a function between 0 and 2 pi. It's the cosine function, 2 cosine x plus 1. So we want to get the range. So let's dust off the cobwebs a little bit with this. So remember, the basic cosine looks like this. This one has an amplitude of 2 and a translation 1 unit up. So what's going to happen to this one here is the mean line goes up by 1. We'll start here at 3, down to 1 to -1. All right, so basically it's going to go like that. So the range, y is an element, so it'll produce y values between -1 and 3 inclusive. Okay, so we've got a transformation written according to this rule. Okay, so this is a transformation from the Cartesian plane to the Cartesian plane. Girls, don't ask me really what that means or why we do it. All you need to do is when you read this, what I would do if I was you guys is write some dashes in those spots there. So we're going to map the graph of y equals f of x, which is this thing here, onto the graph of h of x. Okay, so first of all, we need to state 3 transformations. So let's multiply this matrix out. So x dash is equal to 4x and y dash is equal to -2y. Right, let's see if we can look at the transformation. So x comma y maps to x dash, y dash go up the top. This is going to be -2y. This is going to be 4x. Right, and from here we can read off the transformations just like we did when we determined transformations a few lessons ago. So this is a dilation factor from y. This is a reflection in the x-axis, reflection in the x-axis, and this is a dilation factor to from the x-axis. Right, find the rule, state the domain. Okay, so the rule is going to be, so how do you want to do it? We could do it using transformations, and I think that's probably the best approach. So x dash, not transformations, mapping, given that we've already got the mapping. So our original function is written with an x and a y in it. Our original function, recall, is y equals 2 cosine x plus 1. Just going to write it down, y equals 2 cosine x plus 1. Okay, so what I need to do is make x and y the subject. So x dash on 4 equals x, and y dash over -2 equals y. Right, we're going to pop them in. So y dash over -2 equals 2 cosine x dash on 4 plus 1. Drop your dashes. Why is that a negative? That should be a negative. Just y dash over -2. Okay, so we're going to multiply by -2 on both sides. So y dash is equal to, so -2 multiplied by that is -4 cosine x over 4. And don't forget that when you multiply by -2, it's got to be both of them get multiplied by -2. So -2 multiplied by +1 is -2. All right, state the domain of h of x. Okay, Ms. Cowan loves these types of questions. So the original domain of f of x was 0 to 2 pi, including the 2 pi. So that was the original domain of f of x. So dom f of x is equal to that. So domain of g is going to be affected in some way by these transformations. So dilation factor 4 from the y-axis. So if 0 gets multiplied by a factor of 4, it's still 0. 2 pi gets multiplied by a factor of 4 from y, and that's going to end up being 8 pi inclusive. Reflection in the x-axis will just change the way the graph looks in the x-axis. It won't actually change the domain. Okay, so once it's stretched out to 8 pi, whatever it looks like, when it gets reflected in the x-axis, what will happen is that, like, it'll just go like that, but the domain will be the same. And the same with the dilation factor 2 from the x-axis as well. Just multiply all of the y values by 2. The x values will stay the same. So that will be our final answer. Girls, that would have been done woefully in year 11, and most students in the state will struggle with a question like this. So if you can handle this one here from units 1, 2 methods, you're pretty much going to be able to handle most of what VCAR can throw at you. All right, another question here. Transformation described, so Cartesian plane onto the Cartesian plane is defined by this. Now, this, just some context on this, you must be able to map from a Cartesian plane to something else, and that's why this is here. But we're just going to assume that all transformations in methods are going to be from the Cartesian plane to the Cartesian plane. So, yeah, just assuming that that's going to happen. Okay, so this is x dash and this is y dash, and this is the transformation. So we'll go x dash equals 4 lots of x take 2, noting that we do x take 2 first and then multiply by 4. Y dash equals negative 2 y plus 1. Okay, so what we're going to do is make x the subject, make y the subject, and slam them into that. Okay, x dash on 4 plus 2 equals x, y dash over negative 2 take 1 equals y. Okay, pop it in, and what we have is, I'm going to drop my dashes straight away, y over negative 2 take 1 equals 1 over x on 4 plus 2 all squared. Okay, no way known you can leave it like that, so let's just start to tidy up. Y over negative 2 take 1 equals 1 over, I think the best thing we can do with this is find a common denominator. So that's going to be 8 on 4. So that's going to be x plus 8 on 4 all squared. That's going to be y over negative 2 take 1 equals 1 over x plus 8 squared over 16. When we divide, we're going to multiply by the reciprocal, so it's y over negative 2 take 1 equals 16 over x plus 8 all squared. We're going to add 1. And then we're going to multiply both sides by negative 2, so y equals negative 32 over x plus 8 all squared. Take 2. All right, and there is my resulting function. All right, so on to some VCAR questions, and what I'll do, I'm going to stop this video now and upload this and then record the VCAR questions.